Because I remember the only thing I was thinking that was five of them. It didn't go over LME. I don't remember that.
That's a part of it. It's there. Yeah.
But then it was straight. Just get the angle and you have those degrees and everything. Then you square root it, whatever. That was easy.
Well,
But
that's not
after
good.
everything after that,
That's not bad. That's not bad. All right. Anybody have any questions or y'all good? Oh yeah. Y'all good?
oh, it's too
All right.
I was.
Hmm.
It's like what's this? Oh yeah, it's
I got you. I got you.
You let you get it.
All right, so let's start. Hmm. Just look at what we're getting into today. Bunny rabbits. Yay. All right. So in 1859, an Australian landowner named Thomas Austin released 24 rabbits into the wild for hunting. Because Australia had few predators and ample food, the rabbit population exploded. Ugh. In fewer than 10 years, the rabbit population numbered in the millions. Uncontrolled population growth, as in the wild rabbits in Australia, can be modeled with exponential functions, right? Equations resulting, from those exponential functions can be solved to analyze and make predictions about exponential growth. So in this section, we will learn techniques for solving exponential functions. Cool stuff, cool stuff, cool stuff. All right. In the meantime, if you feel like you know this, knock out your homework. Huh? It's already posted, by the way, so I can take a look at it. So using like bases to solve exponential functions. The first technique involves two functions, right? With like bases, right? Recall that the one-to-one property of exponential functions tells us that for any real number, b, s and t, where b is greater than 0, b cannot be equal to 1, b to the s is equal to b to the t, right? If and only if s is equal to t. So if you have a base raised to some exponent and it's going to be equal to that same base raised to another exponent, right? We can just eliminate the bases and make the exponents equal. Then you just solve for the variable. That's all it's saying, right? Anyway, in other words, right? When an exponential equation has the same base on each side, the exponents must be equal. This also applies when the exponents are algebraic expressions. Therefore, we can solve many exponential equations by using the rules of exponents to rewrite each side as a power with the same base. Then we use the fact that exponential functions are one to one, right? To set the exponents equal to one another and solve for the unknown. For example, consider the equation 3 to the 4x minus 7 power is equal to 3 to the 2x power divided by 3, right? To solve for x, we use a division property of exponents to rewrite the right side, right? So that both sides have a common base of 3. Then we can apply the one-to-one property of exponents by setting the exponents equal to one another. So over here, we have 3 raised to the 4x minus 7 equals 3 to the 2x divided by 3, right? We're going to divide them. And you remember when we divide the exponents, so that turns into subtraction. So now it becomes 3 to the 4x minus 7 is equal to 3 to the 2x minus 1. Because the bases are the same, I could just eliminate them and work with the exponent, right? So it becomes 4x minus 7 is equal to 2x minus 1. Bop, 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 solve for x, and you're done. All right? Questions on this? Simple, right? All right. Let's keep moving. Let me give you guys the theory real quick. So using the one-to-one property of exponential functions to solve exponential equations for any algebraic expression S and T and any positive real number where B does not equal 1, right? The base to the S power is equal to the base to the T power if and only if, right, the exponents S is equal to T. All right? This is good stuff. It's also on your formula sheet in case y'all want to take a look. Just saying. In case you forget. It's all right there. All right, let's look at the first example, right? So solving an exponential equation with a common base, right? So we want to solve 2 to the x minus 1 is equal to 2 to the 2x minus 4 power, right? So I have 2 to the x minus 1 power is equal to 2 to the 2x minus 4 power. Because they have the same base, just work with the numerator. X minus 1 is equal to 2x minus 4. After that, let's solve for it. So subtract x from here, subtract x from here, add 4 over here, add 4 over here. So what do I have? I have 3 is equal to x. Boom. And that's it. Questions on that? Good? All right. Another thing you could do also is you could check it just to verify. Let me just show y'all how to check real quick. You just plug in whatever answer you got into the original. And if you can get the left side to equal the right side, that's all you need. All right. So 3 minus 1, that's 2. And then this is what? 2 times 3, let's call that 6. Minus 4. And it turns out 2 squared is in fact equal to 2 squared. I'm done. I could have kept going. I could have said 4 equals 4, but whatever. As long as you get the left side equal to the right side, you're done. It's that simple. All right. That's how you check your answer. Questions on it, or are we good? Good? Do y'all want to try one, or y'all feel like y'all got it? Want to try one? All right. Here's one for you to try. Yeah, you do. You want it? It's right here. It's take home. Yeah. Y'all can come grab it if y'all want. It's right here.
Everybody gets something to do with this, right?
Just bring back the extras.
Dropping the lowest grade. And you said something about.
Truman? Really?
Graduated from
I heard of them. You just heard the name.
Even did it said. No
Hmm?
I said, so. You said something, you said, if we take access to the student now,
Mm-hmm.
said, we take access to the student lab, right?
Mm-hmm.
With corrections to it. And then what they give us like half grade for that.
Yeah.
Like that.
Mhm. But not for test 3.
Yeah.
Yeah. For test 1 and 2, yeah. 6. Yeah. Monday through Thursday. Yeah. All right. So Did y'all do this already?
Um,
Hmm? Hmm? This is the printer. It makes that mistake sometimes. Hmm. All right, let's go over it. So I have 5 to the 2x is equal to 5 to the 3x plus 2. I have the same base, right? Just work with the numerators. So this becomes what? 2x equals 3x plus 2. What should I do next? No, not yet. So you want to subtract 2x? Nah, that's not the smart way. That's not the smart way. Give me a better answer. So subtract the 3x, right? You want to isolate your variable, right? Subtract 3x. What you do to one side, you do to the other. So now negative x is equal to 2. What do you do next? No. By what? Right. Gonna divide by -1. What you do to one side, you do to the other. So x equals -2. That's it. Questions on that? You good? All right. So bless you. So we want to rewrite equations so all powers have the same base. Sometimes the common base for an exponential equation is not explicitly shown. In these cases, we simply rewrite the terms in the equation as powers with a common base and solve using the one-to-one property. So for example, consider the equation 256 is equal to 4 raised to the x minus 5 power. We could rewrite both sides of the equation as a power of 2, right? Then we reapply the rules of exponents along with the one-to-one property and solve for x, right? So 256 could be rewritten as 2 to the 8th power, and then 4 could get rewritten as 2 to the 2nd power, which is then raised to the x minus 5 power. You remember whenever you raise a power to a power, you multiply, right? So distribute the 2, right? And then now I have the same base. Let's work with the exponent. X is equal to 2x minus 10. Solve for x, right? Boom, boom, boom. X equals 9. All right? Questions on this? All right. Let's keep moving. Let me show y'all how to do this real quick, give y'all some notes. So given an exponential equation with unlike bases, different bases, right? Use the one-to-one property to solve them. So you rewrite each side of the equation as a power with a common base, right? Use the rules of exponents to simplify if necessary so that the resulting equation has the form, right? Base to some power is equal to the same base raised to some other power, right? Use the one-to-one property to set the exponents equal, and then solve the resulting equation, which is the exponents, s is equal to t, for example, for the unknown. Questions? It's good? All right. Let's keep moving. And like I said, the homework's posted for this, so if y'all want to try it, try it over there. But the process is still the same. It's not much different. So now check this out, right? So we're going to be solving equations by rewriting them to have a common base. We're going to solve 8 to the x plus 2 power is equal to 16 to the x plus 8 or plus 1 power, excuse me, to the x plus 1 power, right? So what's a common base that we could use for 8 and 16? What do we think? 2, right? So I could rewrite I could rewrite the 8x plus 2. I could rewrite the 8 as 2 to what power? 3, right? And then imagine that that's going to be raised to an x plus 2 power, right? Maybe I shouldn't have put that there. That should have been like here. That makes more sense. Wait, trying to remember how to write this like that. That makes more sense like that. Okay. Anyway, 16 could be rewritten as 2 to what power? 4, right? So this would be 2, right? To the 4 power, and then raise that to the x plus 1 power, right? Now I have the same base. I can eliminate the base, just work with the exponents. So this becomes what? 3 times x plus 2 is equal to 4 times x plus 1. You already know, distribute, combine like terms, all that good stuff, solve for x, right? Easy stuff. So this is what? 3x plus 6 equals 4x plus 4. Solve for x, right? I'm going to subtract 3x from here. I do the one side, do to the other. I'm going to subtract 4 from here. I do the one side, do to the other. So what's that? 2 equals x or x equals 2. All right? Questions on this? I kind of take for granted that y'all know how to solve for x because I was done in like 28. All right. Y'all feel good or y'all want to see another one? Another one? All right. Good? All right. Here's another example. Try it out. Two-factor thing sucks. All right, let's go. So I have what? 5 to the 2x is equal to what? Mm-hmm. 5 squared. Very good. That should really be something like this, but you get the idea. Same base. This becomes what? 2x is equal to 2 times 3x plus 2. What should I do next? Distribute. All right. So 2x is equal to what? 6x plus 4. Next.
6x.
All right. Good. What's next? Good. Exactly. All right. Good job, everyone. I'll split the script, right? So we'll be solving equations by rewriting roots with fractional exponents to have common bases, right? So this becomes what? 5, excuse me, misspoke. 2 to the 5x power is equal to square root 2. You can rewrite the square root as what? 1/2, right? So this becomes 2 to the 5x is equal to 2 to the half power. After that, they're the same base, set them equal to each other, right? I'm gonna just come over here. So this becomes what? 5x is equal to 1/2. After that, what am I gonna do? Divide by 5, right? So I do to one side, do to the other. So final answer, x is equal to what? 1 over 2 over 5 over 1, keep change flip. 1 over 2 times, what's that? 1 over 5. Call that 1 over 10, right? Questions on that?
So
Good.
just,
Mhm.
we're gonna have to keep waiting for the basic, right?
Mhm.
Oh,
And then solve for numerator. That's it. Yep. Simple, simple, simple. Y'all good or y'all want to see another one? Good? All right. Sorry about that. All right, so question. All right. Do all exponential equations have a solution? If not, how can we tell if there is a solution during the problem solving process? So no, recall that the range of an exponential function is always positive. So while solving the equation, we may obtain an expression that is undefined. All right. So say you see a question like this. Solving an equation with positive and negative numbers, right? I want to solve 3 to the x plus 1 is equal to -2, all right? In this situation, right, there's no value of x that I could plug in here that will give me -2. So this is an example of no solution, all right?
would it,
Go ahead.
would it be a matter then?
Not dealing with imaginary numbers. Yeah. But yeah, there probably would be some imaginary stuff going on. Yeah. All right. Mhm. And that's it. Ain't no solution there. If you want to write the reason why, I'll take that too, because other side is negative and there's no x value that can give me out a negative what you call it answer. But just to show you real quick graphically, all right? This makes the answer kind of pop a little bit more, right? So this graph here shows the two graphs that do not cross. So the left side is never equal to the right side, thus the equation has no solution. So you see the blue line here, that's y equals the 3 to the x plus 1. And this red line is y equals -2. They don't intersect, therefore they have no answer. Right? That's simple. Or said a little differently, there's no value in the equation that I have that can give me a value of -2 as an answer. Y'all good, or you want to see another one? What do we think? I don't hear nothing, so I'm assuming y'all good. All right. So now we're going to talk about solving exponential equations using logarithms. All right. So sometimes a term of an exponential equation cannot be rewritten with a common base. In these cases, we solve by taking the logarithm of each side. So recall that log of A is equal to log of B is equivalent to A equals B. We may apply logarithms with the same base on two sides of an exponential equation. Mhm. So this is a little how-to. So given an exponential equation in which a common base cannot be found, right? This is how you solve for the unknown. Step one, apply the logarithm to both sides of the equation. After that, if one of the terms in the equation has base 10, use the common logarithm. If one of the terms in the equation has the e, that should be an e, not a 10, then use a natural logarithm. All right? Not so bad. After that, use the rules of logarithm to solve for your unknown. That's it. For example, I have 5 to the x plus 2 is equal to 4 to the x power. Now I want to solve this, right? So here's what I'm going to do, right? I have 5 to the x plus 2 is equal to 4 to the x power, right? I want to get that the x is by itself, so I'm going to use the natural logarithm. You could use the regular log too. I like to use natural logarithm since only because it's 2 letters and log is 3 letters. It was less for me to write. That's my only reason. So I have ln of 5 to the x plus 2 is equal to ln of 4 to the x power, right? Now, you remember the rules of logarithm, I can bring the exponent down into the front, right? So I can rewrite this as what? X plus 2 times ln 5 is equal to x times ln 4, right? And then after that, distribute the ln 5 on the left-hand side. So I'm going to have x ln 5 plus 2 ln 5 is equal to x ln 4. All right. Now I'm gonna move the x ln 4 to the other side and the 2 ln 5 to the other side. I'm trying to isolate my variable, right? Isolate my variable. Subtract x ln 4. So I have x ln 5 minus x ln 4 plus 2 ln 5 equals 0. Subtract 2 ln 5. Right? Greatest common factor on the left, factor out the x. What do I have? ln 5 minus ln 4 is equal to -2 ln 5. Divide by it, and I'm good to go. ln 5 minus ln 4 minus ln 4. Now, for me, I'm chill. You could just leave that answer right there and I'm good to go, right? So x equals -2 ln 5 over ln 5 minus ln 4. That's a good answer for me. But if you want, you got the calculator, you could type it in, click enter, get a decimal approximation if you want to. Right? Huh? Oh, yeah. Any questions on this? Up more? Hold on. Huh? Hmm? It's been posted already. Yeah, you can use it. Yeah.
Instead of
Right. You can use whichever one you want. Yeah. Like for me, I like to use ln because it's 2 letters instead of 3. Something else to say, we could have condensed this a little bit further. I would have been cool with this, but if you wanted, you could go a step further to make this ln 5 raised to the -2 power, like that. And on the bottom, you remember that subtraction becomes division, right? So this could have been written as ln of 5 over 4. And in the top, you could have said ln 1 over 25 divided by ln 5 over 4. Any one of those answers I'll take. You know? It's just using the rules of logarithms, that's all. Okay? Yeah, I got you. How about this one? I'm sorry? Not only is the college closed tomorrow, right? I heard that they cutting power to the whole campus tomorrow. So even if you came here, you couldn't do nothing.
From my Saturday. Considering, maybe.
Oh yeah, online. Yeah, yeah.
But you know anybody that's like really good?
All of them.
Yes, I had a
Yeah.
people over there.
Online students. Yeah. Yeah. Nothing Sunday. Monday though, allegedly everything will be back to normal. Allegedly. Hmm. It'd be weird though, like if you go past the college tomorrow, like you'll see no lights. It's like they always have lights on in the college.
There's no nights, it's not nice for one another.
Yeah.
I do bad people.
Like Meister be lit up, you know. Yeah. Yeah.
I felt like something. I'm over there.
Right? Yeah. I mean, like there's wildlife that lives on campus, so they be the ones, chilling.
I don't know, it's stuck like a billion times.
Yeah. Yo, every night I'm leaving here, I see that damn skunk. Every night, yo.
I mean, you chilling.
Man, every time I see him across the street, I'm like, oh, that's your side, my fault. Oh,
Over like the rack fighting for something. I'd rather get like scratched.
I seen there's a couple of raccoons. There's one that yeah,
We have tomato sauce.
you never seen the raccoons?
They still sleep.
Yeah.
They got shot for that.
Yeah, they coming from the library too.
Yeah.
Yeah. Like I think it's Language Hall. There's a skunk that lives there. And in your building, there's a skunk also not a skunk, a raccoon, I mean, that lives there. Yeah. In the bottom of Google.
Really?
Yeah.
Wow, I've never been down there. So.
Yeah.
I heard there's a base down there. I didn't even know that.
That's where they live. Yeah.
Yeah.
They broke out a window and then that's it, man.
You just
They come out and they eat. I don't know. I think they be ordering food and getting it delivered. Well, yeah.
Discount on DoorDash? Oh, told me
I think there's a discount on Grubhub.
Yeah.
Something like that. From what I understand, right? We're supposed to have this thing where like your ID is supposed to be able to be like filled with money, and then you could use that to swipe to buy things on campus, right?
Right.
Not just copies, but even like to buy food and stuff like that. Assuming that we had like a yeah, assuming that we had a cafeteria, but that's supposed to be able to double also on Grubhub, so you can order like stuff.
Is that somebody else? Yeah.
It's supposed to be. It's a yeah. I mean, there's nothing to use it on right now, unless you're getting delivery. So, and copies, yeah. Uh-huh. Interesting. All right, let's take a look. Right. So even though they got different bases, right, I'm gonna still do what I know how to do. ln both sides. You could do whatever you want. I like ln because it's two letters. Now, bring down the exponent, right? So this becomes x times ln2 is equal to x plus 1 times ln3, right? Distribute, combine like to, y'all know what to do, man. Y'all know what to do, right? So this is x ln2 is equal to x ln3 plus ln3, right? Remember, I want to isolate my variable, so I'm going to subtract x ln3. What I do to one side, do to the other, x ln3. So now what do I have? X minus, oh shoot, made a mistake. X ln2 minus x ln3 is equal to ln3, right? Factor out the x. What am I left with? ln2 minus ln3 is equal to ln3. You already know what's going to happen. Divide, right? This is what? ln2 minus ln3. What you do to one side, you do to the other. ln2 minus ln3, right? If you want to go a step further, I would have taken that answer, by the way. But if you want to go a step further, ln 3 over ln 2 divided by 3. Want to call it at that? I'll take that. All right. Questions on this? Good. All right. Not the same question, but an interesting question, right? Say we had 2 raised to the x power is equal to 3 to the x. So they got different bases, but they just raised to plain old x power, right? Is there a number that I could raise any base to that would be the same? What is it? 0, right? Because anything to the 0 power is 1. Boom. Yeah. Yeah, anything to the 0 power is 1. So if it has different bases and they both get raised to 0, you're good. You know? All right, so let's talk about equations that contain E. All right. So one common type of exponential equation are those with base E. My favorite. This constant occurs again and again in nature, in mathematics, in science, in engineering, and in finance. When we have an equation with a base E on either side, we can use the natural logarithm to solve it. All right. Even if it didn't have E, you can still use natural logarithm, whatever. So let's take a look. Give y'all some procedure before we jump into it. So given an equation of the form y equals ae to the kt, which, and let's say you wanted to solve for t, for example, right? How would you do that? You would divide both sides of the equation by a, then you would apply the natural logarithm to both sides, right? To get rid of that e. Then you can just simply divide by k, and boom, you would have t. All right. So let's say, for example, I want to solve this equation of the form y equals ae to the kt power. I'm sorry. Right here? Good. All right. So yeah, so let's say I want to solve this equation of the form y equals ae to the kt. So I want to solve 100 is equal to 20, right? Times e to the 2t power. So long story short, I'm trying to solve for t. Easy. I swear on y'all final, y'all better not get this wrong. Hmm? This just solving for x. That's all this is, right? I'm gonna divide by 20 on both sides. You already know what I do to one side, do to the other. Don't mind me. I'm bad at math. I gotta cross out zeros here. I know 2 going to 2, 1. There's a 5. So this is 5 is equal to e to the 2t, right? So now look, I want to get rid of the e. So what am I gonna do? Natural log that thing, right? So boom, natural log. But what I do to one side of the equation, I gotta do the other side of the equation, right? So boom, ln 5. So now I have what? ln 5 is equal to 2t. After that, divide by 2. You do to one side, you do to the other. This is my final answer. T equals ln 5 over 2. That's it. All right. Questions on this? Good. It does. Yeah. If you want to see why, hold on. Hold on. Let me do another color so it can pop. So ln E, yeah, ln E, right? What that means is it means log base E to the E, right? So essentially, right, what am I asking? Right? I'm asking E raised to some power is equal to E to the 1 power. Right? So X equals 1. That's why it disappears. Yeah. All right. Any other questions? I noticed I did that in the VCC green, right? Yeah. Yo, hashtag go Broncos. A little bit. A little bit. All right, so analysis, right? Using laws of logs, right? We can also write this answer in the form t equals ln square root 5, right? If we want a decimal approximation to the answer, we have to use a calculator. All right, that's it. So what that's saying is this answer that I have here, say it was written as t is equal to 1/2 ln 5, right? Then you could take that to the exponent, and it could be like ln 5 to the half power, and then that's how they got ln square root 5, right? All the same thing. We're just playing with the rules at that point. All right. Y'all good, or y'all want to see another one? Another one? I feel like it's easy. You're just solving for X. Or T, whatever. I guess it's time, so we're solving for T, right? And don't overthink it. It's as easy as you might think it is. Also, for your homework, you can just type it in just like that. You don't need to like whip out the calculator and plug it in and get a decimal number. Like, you could though. You could though. Too much AI. All right, anyway. I have 3 to the E 0.5 T is equal to 11. What should I do? Divide by what? 3. Good. So divide this by 3. I do the one side, do to the other. So now I have E to the 0.5 T is equal to 11 over 3. What should I do next? How do I do that? ln, right? So I'm gonna ln this side, ln this side. So now what do I have? 0.5 T is equal to ln 11 over 3. What should I do after that? By, all right, very good. And that's it. I would accept this answer. If you want to go further and do some other stuff, you can. I'm chilling at this. All right. I guess if you went a step further, it would come out to something like, I don't know, ln 121 over 9, something like that. Well, whatever. Same thing. Right? By the way, all the rules is in the formula sheet, in case y'all didn't know. Right? It's right there. Just use it. Right? I'm only talking about one of the rules right now. Yeah. Oh, sorry. Right here. It's any number. Yeah. All right. Does every equation of the form y equals ae to the kt have a solution? No. There's a solution when k does not equal 0 and when y is equal to a are either both 0 or neither 0. And they have the same signs. So an example of an equation with this form that has no solution is, for example, 2 equals negative 3e to the t. All right. Let's look at another example. Mm-hmm. The log graph.
Basically, log is percent.
Yeah.
Log is what method is that? Whatever log is raised to, it'll be raised to that.
Yeah.
And then ln you said
It's the log with base e.
log basically
Yeah.
is at 2.2.
Something like that. Is it 2.2 or 2.7? I don't even remember. Yeah.
You said you the log base e.
Yeah.
The trick that's
Yeah. I don't know. Maybe it'll come back to you as I'm going through it. Yeah. Let me see this one. Huh? It's 2 point something. I don't remember. Yeah. 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 I mean, if you go on your calculator and you click E and then click enter, it'll tell you what the number is. I don't remember off the top of my. I know it starts with 2 though. Yeah. Oh, ln has 2 letters. It's easier for me to write. Yeah. Log is 3 letters. Yeah. Yeah. Yeah, log base E. Yeah.
But they both get rid of the e.
Both. Yeah. Well, no, E is only getting rid can only be gotten rid of with ln, not log. But there is a way to get rid of it with log. You know, it's more complicated, but there is a way. Yeah. Yeah. I mean, you could just use ln for everything. I mean, ln is the truth, man. Yeah. Yeah. You know? All right, let's look at this. This might look complicated, but it's not that bad. This is 4e to the 2x plus 5 is equal to 12. Long story short, just solve for x, right? Subtract 5 from over here, where we do to one side, we do to the other. 4e to the 2x is equal to, oh Lord, what's that, 7? All right, thank you, appreciate that. Then you want to divide by 4, which is the one side you do to the other. So now I got e to the 2x is equal to, what's that, 7 over 4? ln both sides, get rid of that e. So ln. So now I got what? 2x is equal to ln 7 over 4. Divide by 2, call it a day, that's it. So this is x equals ln 7 over 4 divided by 2. And that's it. Questions on this? Excuse me, questions on this? All right. Y'all want to see another one, or y'all feel like y'all good? Another one? I'm sorry, you want to see something? Is it go down or up? I'm sorry. Yeah. Oh, this way? You're welcome. So here's another one. All right, let's try it. So I'm just trying to solve for t. That's all I'm doing, right? So what am I gonna do first? Mm-mm. What should I do first? Before you do that, anybody? No. Just solve for t. Right. So I'm gonna minus the e to the 2t. What I do to one side, do to the other. Right? So now what do I have? 3 equals 7 minus 1, 6 e to the 2t. All right? Divide by 6 both sides. 1/2 equals e to the 2t. Now, ln both sides. What do I have? ln 1/2 is equal to 2t. Divide by 2, where we do to one side, we do to the other. That's it. Questions on it? All right, now let's talk about extraneous solutions, right? So sometimes the methods used to solve an equation introduce an extraneous solution, which is a solution that is correct algebraically, so when we solve for it, but it does not satisfy the condition of the original equation, right? One such situation arises in solving when the logarithm is taken on both sides of the equation. In such cases, remember that the argument of the logarithm must be positive, right? If the number we are evaluating in a logarithm function is negative, there's no output. All right? That's simple. So try this. Solving exponential functions in quadratic form, we have e to the 2x minus e to the x is equal to 56. Let's try this out. I have e to the 2x minus e to the x is equal to 56. First thing I want to do, subtract 56 from both sides. Now I have e to the 2x minus e to the x minus 56 is equal to 0. Right after that, you want to factor this, right? Give me two numbers that multiply to 56 and add up to -1. 11. Two numbers that multiply to 56 and add up to -1. Or multiply to -56. That's it, right? So I can rewrite this, right, as e to the x minus, what's it, 8x, 8x, excuse me, minus 8 times e to the x plus 7, right? That equals 0. Not bad, right? And then after that, just solve for x in both terms. It wouldn't be the same?
Yes. That's 2x.
EX squared, and when you raise the power to a power, you
What's
so look, e to the x squared, right? When you raise the power to a power, what do you do to the exponents? No, not add them, multiply them, right? So this becomes e to the 2x. Yeah, yeah,
Okay.
yeah. But back to this one over here. Uh-huh. Right. Treat it like an x. The e to the x is treated like an x, and it comes out like this. After this, set both of them equal to 0. Now here's the thing, right? Add 8, subtract 7, subtract 7. All right. And then after that, ln both sides, boom, 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 right? However, here's the problem that I have here. You see when I ln this side, no problem. X equals ln 8. Good to go, right? Well, with the other side, there's no solution, right? So this is an extraneous solution. Because it equals -7, it's impossible. No? So we just have the x ln 8. That's it. Any questions? Okay. So when we plan to use factoring to solve problems, we always get 0 on one side of an equation because 0 has the unique property that when a product is 0, 1, or both of the factors must be 0, we can reject the equation e to the x is equal to -7 because a positive number never equals a negative number. The solution ln of -7 is not a real number. And is the real number system, this solution is rejected as an extraneous solution. Right? Plus that. So does every logarithmic equation have a solution? No. Keep in mind that we can only apply the logarithm to a positive number, right? Always check for extraneous solutions. Mhm. Now we want to talk about using the definition of a logarithm to solve logarithmic equations. So we have already seen that every logarithmic equation of log some base of x is equal to y is equivalent to the exponential equation b to the y power is equal to x, right? So we can use this fact along with the rules of logarithms to solve logarithmic equations where the argument is an exponential expression. For example, consider the equation log base 2 of 2 plus log base 2 of x 3x minus 5 is equal to 3. To solve this equation, we can use the rules of logarithm to help to rewrite the left, right? The left side in compact form and then apply the definition of logs to solve for x, right? So log base 2 of 2, right? Plus log base 2 of 3x minus 5 equals 3, right? If we apply the log rules to them, right? We have technically have log base 2 raised to the 2 times 3x minus 5 equals 3. And then raise both sides to base 2. And then now you have 2 to the third is equal to 6x minus 10. We good to go right there. Just solve for x. Add 10, then square root, whatever, 6. Boom. Or if you don't need to, you just divide it, whatever. Y'all get the idea. Just solve for x. That's all it is. Let me give you that definition again real quick. So using the definition of a logarithm to solve a logarithmic equation, for each algebraic expression S and real numbers B and C, where B does not equal 0, C cannot equal 0, the log, right, base B of S is equal to C, if and only if B to the C is equal to S. Try that out. All right. I have 2 ln x plus 3 is equal to 7. What do I do first?
Exactly.
Good. What should I do after this? So now I have ln x is equal to 2. What should I do after this?
Exponential.
Raise this to base b. What should I do one side, do to the other? So now x is equal to e to the second. Questions about this? All right. So I raised both sides to the base e because remember, natural log is log base e to get rid of it on the left-hand side. That was my ultimate goal. Yeah, to solve for x. Like final answer. Yeah, final answer. Hmm. How y'all feeling? Y'all good? Or y'all want to see another one? Yeah. Even easier because you're just solving for it. Right? Yeah. Sure. Mhm. Mhm. Be back. I'll let y'all try the next one. Same idea, just solve for x. I'll be back. but it has something that might help if you don't have a calculator. There's websites you can use like Desmos. Desmos is an online graphing calculator if you want. You know, yeah, it's not good. Yeah, it's a website. Yeah, just kind of type it in. It gives you a table of values, all that stuff. Yeah. All right, easy question. 2 ln 6x equals 7. Divide by 2, divide by 2. ln 6x is equal to 7 over 2. Right? Get rid of this. 6x is equal e to the 7 over 2 power, divide by 6. Divide by 6. X equals e to the 7 over 2 divided by 6. Questions, anybody?
I did this for like
Mhm.
3 years before that's
All right.
so what I learned, the question really to learn is to learn times exact, and then I divide it for both sides and then try to go there.
No. ln is attached to the 6x. The 2,
Oh, it's that too.
no. It's like 2 times ln 6x. Yeah. ln is a function itself, you know? Yeah. I feel you, man. So E is to undo on the ln, yeah. Yeah.
That's like a square root thing? See, like,
E?
not square root, it's a.
Yeah, it's an inverse. Yeah. E is an inverse to ln. Yeah. All right, so using the one-to-one property of logarithms to solve logarithmic equations. As with exponential equations, we can use the one-to-one property to solve logarithmic equations. The one-to-one property of logarithmic functions tells us that for any real numbers x greater than 0, right, s has to be greater than 0, t has to be greater than 0, and any positive real numbers where b does not equal 1. So if we have log of base b of s is equal to log of base b of t, right, if and only if s is equal to t. So for example, if log base 2 of x minus 1 is equal to log base 2 of 8, then because they're the same log, same base, I could just deal with what they're going to. So x minus 1 is equal to 8. Bop, 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 solve for the x. That's it. Right? So if x minus 1 equals 8, then we can solve for x, right? And we get x equals 9. To check, we can substitute x equals 9 into the original equation. Log base 2 of 9 minus 1 is equal to log base 2 of 8, which is equal to 3. In other words, when a logarithmic equation has the same base to each side, the argument must be equal. This also applies when the arguments are algebraic expressions. Therefore, when given an equation with logs of the same base on each side, we can use rules of logarithm to rewrite each side as a single logarithmic, right? Then we use the fact that logarithmic functions are one-to-one to set the arguments equal to one another and solve for the unknown. All right? So not too bad. So for example, consider the equation log of 3x minus 2, right, minus log of 2 is equal to log of x plus 4. To solve this equation, we can use the rules of logarithms to rewrite the left side, right, as a single logarithm, and then apply the one-to-one property to solve for x, right? So log of 3x minus 2 minus log of base 2 is equal to log of x plus 4, right? You remember that minus becomes division, so this can be rewritten as log of 3x minus 2 over 2 is equal to log of x plus 4. Now we can get rid of the logs because they're the same and just work with the numerators. So we have 3x minus 2 over 2 is equal to x plus 4. Maybe we might want to multiply by 2 on both sides to get 3x minus 2 is equal to 2x plus 8. Solve for x, bam, 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 equals 10. Right? To check the results, you could just plug in the 10 to see if it works. Yada, yada, yada. Y'all get it. So using the one-to-one property of logarithms to solve logarithmic equations. So for any algebraic expression S and T and any positive real number B where B does not equal 1, the log of base B of S is equal to the log of base B of T if and only if S is equal to T. Note, when solving an equation involving logarithms, always check to see if the answer is correct or if it is an extraneous solution. All right. I mean, yeah, if it's negative, it's not gonna work. But if it's positive, then you know. If you get like two answers and one is negative, one is positive, the answer is the positive one. What? Yeah. We'll see. All right. This little how-to. So given an equation containing logarithms, solve it using the one-to-one property. So you want to first use the rules of logarithms to combine like terms if necessary, so that the resulting equation has the form log base b of s equals to log base b of t, excuse me. Use the one-to-one property to set the arguments equal. and then solve the resulting equation, right? Equation, yeah, S equals T for the unknown. That's it. You guys try. Good. All right. So not bad. You have ln of x squared is equal to ln 2x plus 3. Very simply, I want to get rid of the ln, so I'm going to make it base e. Bam, bam. X squared equals 2x plus 3. You already know what to do, right? Subtract the other side, factor, get the answer. Y'all know how to do this, right? This is going to become what? X squared minus 2x minus 3 equals 0. X minus 3, x plus 1 equals 0. X is equal to 3 and negative 1. And that's it. Questions on this? It's literally that simple. You can verify by plugging it in, and seeing that it works. That's it. Mhm. When I'm raising it to the power, like I'm whatever. So yeah, yeah. So there are two solutions, 3 or negative 1. The solution negative 1 is negative, but it checks when substituted into the original equation because the argument of the logarithm function is still positive, right? So even though when I plug in, I'm plugging in a negative 1 to check, it doesn't change the answer. The answer becomes back positive, so we're good to go. Yeah. It's only a number that won't make the inside negative. As long as the inside remains positive, you're good to go. Yeah. Yeah. Like when you plug it back in, it has to work. Like the inside has to be positive. Yeah. Yeah. And when you're on the test, you can actually plug it in and see the calculator will return to you a error message if it doesn't work. You know, it's another way to do it. Try this one. Even though I know you guys, I feel like you guys got it. Just try this.
How could I pass?
You pass what?
How could I pass the seats in the?
I don't know. I hear tomorrow is gonna be a whole bunch of rain, so maybe everybody's preparing for that. Yeah,
Yeah.
like in the afternoon though, not the daytime. That means good sleep tomorrow night. Yeah. In the rain, yeah. All right, let's check this out. ln of x squared is equal to ln of 1. I'm going to base e it to get rid of the ln. So I have x squared is equal to 1. You already know. Square root both sides. X equals plus or minus 1. Right? Now, why does this work? If I plug in positive 1, I still get a positive 1 out. If I plug in negative 1, I still get a positive 1 out. So that's why it's cool. All right?
Crazy, and then. Crazy, and could be pretty much the square and bracket.
Yeah. They're inverses to each other. Exactly. Yeah, yeah. ThinkPad? Nah. Let me see. I'm gonna Google it. I haven't seen it.
Literally like unfolds flat. It's really like old concept.
Mhm. What's it called?
It's the actual something is the versus the
Let me see.
literally I said has the most advanced process.
Interesting.
It has like it has a better process.
That's fire. X1? Is that it? I think it's it.
I think there's two of them. I think there's an X one and an X, I think the X one. There's there's literally one that is more expensive, but has like less incident. See,
Got you.
yeah, it has like a much less graphic part, it's not as, yeah, it's not as like, it's like, there's one that's like, it comes like $2,000 or something.
I see it here. There's two of them. One is 2,200. The other one is 2,600.
That's okay. The one that's 600, I think,
That's
that's the stuff feature that it's 2,200. That's what I'm saying. From the work. Excuse me, the break, I think it was.
but the 2,600 is the new one. Yeah.
That's.
It's kind of small though. It's similar to this one that I have.
Yeah, no, that's what I actually need.
Yeah.
Travel.
Yeah.
I think.
Yeah.
Yeah, just a little side one.
You know which one was fire? Microsoft Surface Go, Go, right? It was small. I mean, not phone small. It's a laptop, but it was small. You know, like smaller than this. Yeah, that joint was nice. It was. I think the most expensive version of it was 300. You know, so it wasn't too bad. It has the pen you can write with it and all that. So yeah. All right, let's keep moving. Story time. All right. So a golfer swings to hit a ball over a sand trap and onto the green, right? Taka Taka Woods. So an airline pilot maneuvers a plane towards a narrow runway. A dress designer creates the latest fashion. What do they all have in common? They all work with angles, right? And so do all of us at one time or another. Sometimes we need to measure angles exactly with instruments. Other times we estimate them or judge them by eye. Either way, the proper angle can make the difference between success and failure in many undertakings. So in this section, we will talk about the properties of angles. All right. I feel like everybody in here drives, so y'all probably know this whole lesson already. Well, this is parallel parking. That's all this is, man. Set up that mirror, bam, bam, and we good to go. Mhm. So we're gonna build up to it though. We gotta go step by step. So drawing angles in standard position, right? Properly defining an angle first requires us to define a ray. All right. So a ray consists of one point on a line and all points extending in one direction from that point, right? So the first point is called the endpoint of the ray. We can refer to a specific ray by stating its endpoint and any other point on it. The ray in this picture, right, can be named as the ray EF, right? E being your endpoint, F being wherever else, right? Or in symbol form as e to the F. All right. It's another way to write a ray. So now that we know what a ray is, I'm talking about Ray Charles. All right. Let's talk about what an angle is. All right. So an angle is the union of two rays having a common endpoint. So the endpoints together are called a vertex. All right. So the vertex of an angle, right? And the two rays are the sides of the angle. So the angle in this picture right here is formed from ray ED and ray EF, right? they both connect at E, making the vertex, right? So angles can be named using a point on each ray and the vertex. So such as angle DEF, right? DEF. Or you can sometimes write it in a form like angle DEF like this, right? A lot of times in textbooks, you're gonna see it more like this. Just let y'all know, right? Greek letters are often used as variables for the measure of an angle. So this table right here will show us a list of Greek letters commonly used to represent angles, and a sample angle is shown in the next figure, right? So this first one right here looks like a 0. That's theta, right? Then over here we have phi, right? Then we have alpha, beta, and gamma. Just showing y'all. I know for me, I didn't really see all of those letters until much later in math, but you guys gonna get to see it early today. You know? So just to show you the figure, this is how they would come together, so to speak, right? So as you can see, the angle itself is the Greek letter, and it's in between, right? The two rays, right, that are connected at the same endpoint, right? That's the angle right there. So this is called angle theta. So, mhm. Good stuff, good stuff. All right, next. So angle creation is a dynamic process. We start with two rays lying on top of one another. We leave one fixed in place and rotate the other. The fixed ray is called the initial side, the starting point, right? And the rotated ray is the terminal side, right? So in order to identify the different sides, we indicate the rotation with a small arc and an arrow close to the vertex. So here's your initial side, right? This doesn't move, right? And then as we come away from it, right? This is our terminal side where we're going to stop at. That's the terminal side, right? And then this arrow right here indicates that it's moving, right? Questions on this so far? You good? So as we discussed at the beginning of this section, there are many applications for angles, but in order to use them correctly, right, we must be able to measure them. The measure of an angle is the amount of rotation from the initial side to the terminal side, right? Probably the most familiar unit of angle measurement is the degree. 1 degree is 1/360 of a circular rotation. So a complete circular rotation contains 360 degrees. An angle measured in degrees should always include the unit of degrees, right? After the number or included the degree symbol, that little circle thing. I don't even know if we call that, but that means degree, right? So for example, 90 degrees is equal to 90 with a little circle, which means 90 degrees. All right. Not sure what that's called. I'm also not sure how to get on the keyboard either. You know, that's another thing. Yeah.
Yeah, I wasn't
Yeah. That one is hard to come by. Yeah. I mean, I guess if you do 0.75 of a dollar, that kind of means 75 cents, I guess. Yeah. Yeah. All right. So To familiarize, right, our work, we will begin by drawing angles on the XY coordinate plane. Angles can occur in any position on a coordinate plane, but for the purpose of comparison, the convention is to illustrate them in the same position whenever possible. An angle is in standard form if its vertex is located at the origin and its initial side extends along the positive x-axis. So right here is the origin in the middle. Our initial side goes out right here. And our terminal side, all the way over here, that's our terminal side. Right? Questions on this? I'm gonna be asking y'all to draw these for me. Okay.
And so, how do I do that?
Yeah.
Okay, then that's just-
No, it gets simple. I promise. I'm gonna show you. Don't worry. So if the angle is measured in a counterclockwise direction, counterclockwise, from the initial side to the terminal side, the angle is said to be a positive angle. But if the angle is measured in a clockwise direction, the angle is said to be a negative angle. All right? Just in case I didn't know,
They measure the positive and negative of and based on the y-axis.
It's based on the rotation.
Okay, so-
Yeah. The y-axis would tell you more like what is the radius of it, right? For like the unit circle. By the way, didn't even tell y'all this, but y'all have the unit circle. It's in your formula sheet. So drawing an angle in standard position always starts the same way. Draw the initial side along the positive x-axis to place the terminal side of the angle. We must calculate the fraction of a full rotation the angle represents. We do that by dividing the angle measured in degrees by 360, right? So for example, to draw a 90-degree angle, we calculate 90 divided by 360, which is equal to 1/4. So the terminal side will be 1/4 of the way around the circle, right? Moving counterclockwise from the position from the positive x, right? We draw the 360 angle and calculate 360 divided by 360 is equal to 1. So the terminal side will be one complete rotation around the circle, right? Moving counterclockwise from positive x in this case, the initial terminal side will overlap. So here you go, right? If I'm drawing a 90-degree angle, I have my initial side right here, and I'm gonna go until I hit 90 degrees, which is going to be right there on the y-axis, right? For 360, right, I'm going all the way around, right back to where I started from, right? That's 360. That's like a full rotation right there. And that's it. Questions on this? Yeah. Yeah. Okay. Yeah.
We always write that as 350 measure of
So what you're talking about is coterminal angles, yeah. We're gonna get there, yeah. Yeah. All right, since we define an angle in standard position by its initial side, we have a special type of angle whose terminal side lies on the axis, right? A quadrilateral angle. Can't even say that word. This type of angle can have a measurement of 0, 90, 180, 270, or 360. For example, this first ray right here that we have, our initial side, this is 0 degrees. Going straight up, is 90 degrees, right? On the other side is 180. And down the middle, downwards is 270. And then 360 would actually be right back over here where we started from, because that's a full rotation. Right. And there's a 4 quadrants. So the quadrantal angles are angles in standard position whose terminal side lies on the axis, including 0 degrees, 90 degrees, 180 degrees, 270 degrees, or 360 degrees. Okay. Bless you. So let me give you a little how-to. So given an angle measure in degrees, draw an angle in standard position. So here's how you do it. First, you want to express the angle measure as a fraction of 360, reduce the fraction to simplest forms, and then draw an angle that contains that same fraction of a circle beginning on the positive x and moving counterclockwise for positive angles and counterclockwise, right? I mean, regular clockwise, excuse me, for negative angles, right? Now, technically speaking, this procedure is something I would expect a computer to do, right? To know that, all right, 90 degrees is 1/4 of a circle, right? I'm not interested in all of that, right? Yeah, just do your best. Yeah, yeah. I don't even need y'all to calculate all that. What I need y'all to do is just draw it for me, right? So let's look at A, right? A says sketch an angle of 30 degrees in standard position. Here you go. You have your XY plane right here. Bam, right? Little line in between. And I'm telling you that this angle right here, this 30 degrees. I'm done. That's it. Any questions on that? You good? Yeah. Yeah. Uh-huh. Uh-huh.
You're not looking to see any.
Yeah, just draw it. Yeah. Let's look at B. I'm gonna change up my color just because of space. Oh geez, what am I gonna choose? All right, let's do purple. Let's do purple. All right. So for B, all right, I have X, I have Y, all right. Get a little bit larger. So I have negative 135, right? So I know that 135 is less than 180, right? And I know where 180 is, right? This is 0, this is 90, this is 180, this is 270, right? 360. Technically, I should have done that on the other one, right? Because I'm going in reverse. But it's all right. Let me go in reverse with the negatives for y'all. 0 still is there. I didn't mess up on 0. This is negative 90, negative 180, negative 270, and then negative 360. So now they said they want negative 135, right? So 135, which quadrant that's going to be in? Yeah, the bottom left. Good. All right, third quadrant right here. So this is your angle for 135. I'm trying to think where I'm going to put it. I'll put it right here. 135 degrees. There you go. That's it. Yeah, because it's negative, right? Negative goes backwards, positive goes, wait, I'm saying that the wrong way. Hold on. Positive goes backwards, right? And negative goes forward. Yeah. All right. But let me label the other one just to be fair, real quick. This is 0 degrees, 90, 180, 270, right? And then this is 360. How did it say it again? 30 degrees? Oh, they asked me right here. On the graph? Honestly, I don't know. I know that 30 is between 0 and 90. That's it. Yeah. It should have been smaller, yeah, but I'm not an artist, you know. No, it's right here. 0 is here, and then 90 is up here. Okay, so for the purple one now, this is for negative, right? The purple is negative, so that's why they start over here. So 0, 90, -1, excuse me, 0, -90, -180, -270, -360. Yeah. So if it was -30, it would have been in this quadrant here, the fourth one. Yeah. Yeah. Right. Yeah. So that's it. That's all I'm really looking for from y'all. Hold on 1 second.
Yeah, we are like still living in society where we took like much time up there, stuff like that. The second time.
True. But we have computers, you know? Now we have AI. You know, how great is that? I'll let you guys try this. And oh my God, don't just draw a ray that don't have no number for the angle or nothing. Like that's straight 0 right there. Um, this depends on which way I'm going. This one's positive though, so goes counterclockwise. Right. Yeah. It depends on the question. Yeah. All right, so let's do this one, right? So there we go. This is X and Y. This is 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then 360 degrees. They asked me for 240. Which quadrant am I in? Third quadrant, right? There we go. Boom. It's 240 degrees.
Yeah, this is back to that.
That's because he drives. That's why you know this way. Yeah. Yeah. If you drive, this is nothing, you know? Yeah. All right, let's talk about converting between degrees and radian, right? So dividing a circle into 360 parts is an arbitrary choice, although it creates the familiar degree measurement, we may choose other ways to divide a circle, right? So to find another unit, think of the process of drawing a circle. Imagine that you stop before the circle is complete. Excuse me. The portion that you drew is referred to as an arc, right? So an arc may be a portion of a full circle, or more than a full circle, represented by more than one full rotation. The length of an arc around an entire circle is called the circumference of that circle, right? Good stuff, good stuff, good stuff. Just gonna mention this. Not gonna test y'all on this, but just good information to have, you know? All right, so the circumference of a circle is C is equal to 2 pi r, right? If we divide both sides of the equation by r, we create the ratio of the circumference to the radius, which is always 2 pi regardless of the length of the radius. So the circumference of any circle is 2 pi, which is something like 6.28. It's missing some decimals, but you guys get the idea, right? Times the length of the radius. That means that if we took a string as long as the radius and used it to measure consecutive lengths around the circle, there would be room for 6 full string lengths and a little more than a quarter of a seventh, as shown, right? So boom. This is like showing you how to derive the circumference, right? So it would be about 6 pieces of string, right? And then divided by like 7 or something. It's interesting. That's for another day and another class. All right. Anyway, here's what we care about. All right. So to bring us to our new angle measure, 1 radian is the measure of a central angle of a circle that intercepts, an arc equal to the length to the radius of that circle. A central angle is an angle formed at the center of the circle by 2 radii, right? Because the total circumference equals 2 pi times the radius, right? A full circular rotation is 2 pi radians. So here's what I need y'all to know. 2 pi radians is equal to 360 degrees. Pi radians is equal to 180 degrees. And 1 radian is equal to 180 degrees divided by pi, or whatever, 57.3. I don't really care about that decimal thing. Huh? It is. Yeah.
That's right.
Really?
I haven't checked, I didn't see it. I knew it was 180 something, but I don't know where the cleanup was.
It's there. Look again. It's in the announcements too. If you don't have it. All right. So note that when an angle is described without a specific unit, it refers to a radian measure. For example, angle measure of 3 indicates 3 radian. In fact, radian measure is dimensionless, since it is the quotient of a length circumference divided by the length of the radius, and the length unit cancels out, right? So the angle T, here's T, right, sweeps out the measure of 1 radian, right? Note that the length of the intercepted arc is the same as the length of the radius of the circle. So what they're saying is that this radius right here, R, is the same thing as this arc length right here for R. That's what it's describing. All right, so let's talk about relating arc lengths to radius. An arc length S is the length of the curve along the arc. Just as the full circumference of the circle always has a constant ratio to the radius, the arc length produced by any given angle also has a constant relation to the radius regardless of the length of the radius. All right. All right, it's about to be good right here. All right, this ratio called the radian measure is the same regardless of the radius of the circle. It depends only on the angle. This property allows us to define a measure of any angle as the ratio of the arc length S to the radius R. Here's our magic formula right here for arc length. S equals R theta, right? Or this one on the bottom is just you solving for theta, like you divide by R on both sides, whatever, right? So since S equals R, then theta equals R over R equals 1 radian, right? So here you go. 1 radian would be right here. This would be 2 radians around and the full rotation, all right? So in an angle of 1 radian, the arc length S equals the radius R. B, the angle of 2 radians has an arc length of S equals 2R. A full rotation is 2 pi or about 6.28 radians. All right. All good stuff.
What do we do about that? Find out what it means.
Like that could be a question. Like I might give you an arc length and give you a radian, and then I ask you what is the degree. That's possible, or is something else, you know? Yeah. So to elaborate on this idea, consider 2 circles, one with radius 2 and the other with radius 3. Recall the circumference of a circle is circumference equal to 2 pi r, where r is the radius. The smaller circle then has a circumference of 2 pi times 2, which is equal to 4 pi, and is larger than the circumference of 2 pi times 3 equals 6 pi. Now we discuss a 45-degree angle of 2 circles. There you go. All right. So a 45-degree angle contains 1/8 of the circumference of a circle, regardless of the radius. All right. So what they're trying to show you here is that these angles, right? The angle itself is the same, right? Regardless of how far out the radius is. You know? So notice what happened if we find the ratio of an arc length divided by the radius of the circle. Smallest circle is 1/2 pi divided by 2, or is equal to 1/4 pi. The largest circle is 3/4 pi divided by 3, or 1/4 pi, right? Since both ratios are 1/4 pi, the angle measures of both circles are the same, even though the arc length and radius differ. Right? Let's talk about radians. So 1 radian is the measure of the central angle of a circle such that the length of the arc between the initial side and the terminal side is equal to the radius of the circle. A full rotation, 360, equals 2 pi radians. A half rotation is 180 degrees, is equivalent to pi rotations, right? Radians, excuse me. The radian measure of an angle is the ratio of the length of an arc subtended by the angle to the radius of the circle. In other words, if S is the length of an arc of a circle and R is the radius of the circle, then the central angle containing that arc measures S over R radians. In a circle of radius 1, the radian measure corresponds to the length of the arc. Right? All right, so question. A measure of 1 radian looks to be about 60 degrees. Is that correct? Yes, it's approximately 57.3 degrees because 2 pi radian equals 360. 1 radian equals 360 divided by 2 pi. Very simple. Because radian measures is the ratio of two lengths, it is a unitless measure. For example, in figure 12, suppose that the radius were 2 inches and the distance along the arc were also 2 inches. When we calculate the radian measure of the angle, the inches cancel and we have just the result without units. Therefore, it's not necessary to write the label radians after a radian measure. And if we see an angle that is not labeled with degrees or the degree symbol, we can assume that is a radian measure. All right. Consider the most basic case, the unit circle, a circle with radius 1. We know that 1 rotation equals 360 degrees, right? We can also track 1 rotation around a circle by finding the circumference, right? Which is again 2 pi r. And for the unit circle, the circumference is actually just 2 pi, right? These two different ways to rotate around a circle give us a way to convert from degrees to radians. So 1 rotation, 360 degrees, is equal to 2 pi radians. Half a rotation is equal to 180 degrees, which is pi radians. 1/4 of a rotation is 90 degrees, which is pi over 2 radian. All right. All right. So identifying special angles measured in radians. So in addition to knowing the measurement in degrees and radians of a quarter revolution, a half revolution, and a full revolution, there are other frequently encountered angles in 1 revolution of a circle with which we should be familiar. It is common to encounter multiples of 30, 40, 60, and 90, right? These values are shown in the figure. Memorize these angles and it will be useful when we study properties associated with angles. Full disclosure, I didn't memorize any of this, you know? Y'all want to memorize it, y'all memorize it, you know? Y'all don't gotta memorize it though, because guess where it is? Yep, on the formula sheet, right? But here it is. All right, let's take this to another level real quick. All right. Huh? No. So now we're gonna go with the angles real quick, just to make it pop a little bit. All right. So now we can list the corresponding radian values for the common measures of the circle corresponding to those listed, right? And here they are right on top of each other. So you have 0 degrees and 2 pi. Well, no, just say it was 0, right? 30 degrees comes after that, or pi over 6. Next is 45 degrees or pi over 4. After that, it will be 60 degrees or pi over 3. 90 degrees or pi over 2, 120 degrees or 2 pi over 3, 135, 3 pi over 4, etc. All right. So the numbers with the pi's in it, those are radian measures, right? The ones with the degrees, those are degree measures. All right. For me personally, I'm not really a radian person. I'm more of a degree person. I understand degrees. So whenever I get a question that is in radian, I will flip the radian to degrees, answer it the way I know how to answer it, and then flip the answer back to radian to get my full credit. You know?
And
So
and like the answer to me, is that, you know, it's more like,
some of them will. Yeah, depending on what they're asking you to do. You know? So that being said, let's talk about converting. So converting between radian and degrees, because degrees and radian both measure angles, we need to be able to convert between them, right? We can easily do so using a proportion. Theta over 180 is equal to the theta r that we're looking for divided by pi. This proportion shows that the measure of an angle theta in degrees divided by 180 equals the measure of the angle theta in radians, right? Divided by pi. Or phrased another way, degrees is to 180 as radians is to pi, right? So long story short, if I give you some kind of radian measure and I ask you, like, convert this to degrees, right? You multiply it by 180 over pi, right? If I give you a radian measure, 3 pi, I'm just making up something off the top of my head, right? And I wanted you to convert that to degrees, you multiply that, right? Times 180 over pi, the reverse of it. That's it.
We determine which degree will be very soon based on which section it's in. So if it's in the 90 degree, we using that to find out what function it is.
Like, what is it in radian, right? Yeah. They'll always tell you that. Always tell you that.
Each section.
Yeah,
Deal with something in that section,
right. I got you. So converting between radian and degrees, here you go. There's your formula again, right? Multiplied by pi over theta, over 180, right? Is equal to the theta in radian over pi. Huh? Yeah. No, from radian to degrees. So now we want to convert these radian measures into degrees. Let's look at A. A is pi over 6. All you have to do, multiply this by 180 degrees divided by pi. That's how you go from radian to degrees, right? Radian to degrees. So when you multiply straight across, these cancel out. 6 goes into 6, 1. 6 goes into 18 how many times? Like 3 times, right? So call this 30. Yeah. So my answer for pi over 6 is 30 degrees. Done. That's it. All right. You could do that in the calculator. You don't gotta be reducing it like I'm doing it. I don't have a calculator, that's why you see me reducing it. All right. Right? Same thing here. All right, same thing with this next question, right? Let's look at B. Let me change my color real quick. So for B, I got 3, but that 3 I'm telling you is in radian, and I want to go from radian to degrees. So I'm going to multiply by the same thing, 180 over pi, straight up, right? So then now what's going to happen here, right? Just multiply straight across. Don't even think about it, right? 180, 180, I know that's 360. 360 and 180 is what? 540? All right. So that's 540 degrees over pi. If you have a calculator, you could divide it and get some other number, but whatever. This is what I would take. That's simple. All right. Web work will take that too. You know?
Yeah.
Mhm.
I just want to simplify, man.
That's simplified for me. I'm good. Let you guys try one. Nothing crazy. You have a negative 3 pi over 4. And we want to convert that to degrees. We good?
Oh, yeah.
Alright. Yeah. I know if you got test 3 already, but it's test 3. Let's take home. So let's do it. So I want to convert from radians to degrees. I have -3 pi over 4. So I'm going to multiply this by what? 180 over pi. Very good. Pi's cancel. 4 goes into 4 once. 4 goes into 80. What's that? 45 times? Something like that? I don't know. All right. And then 45 times -3. What is that? Negative.
That's fine.
45?
Yeah, you get 135.
Oh, 135. All right, appreciate that.
135.
All right, so then that's it. I'm good. All right. Appreciate it. All right, let's do the reverse real quick. Make me feel good. So converting degrees to radians, right? So I want to convert 15 degrees to radian, right? So I have 15 degrees. I don't know how 15 became 50, but I have 15 degrees, right? I'm going to multiply that by what? Over, right? So pi over 180, right? And then you just go ahead and do that. I'm trying to think. That's 15. What's 15 over 180? What y'all got? I don't even know. 5 going to 15. What's that? Like 3 times? And 5 going to 180, how many times? I don't even know.
Well,
36. I really didn't know. But yeah, 12. You're right. So 3 goes into 3 once, 3 goes into 36 12 times. Bam. So what's my answer? Pi over 12. That's it. All right. Can't beat that. All right.
what's the significance of any
180 degrees. So that's like a half turn. You know, like imagine like I'm facing you, like if my back was to you, that's 180. You know, it's like a half turn.
But like, let's say like, you had, only and was, I don't know, 197.
Okay.
We wanted to use the, what is it, the 2.8? What do you use that, multiple times that still use 180?
No, we still got to use the pi over 180 if we're gonna convert that to radian. You know? Yeah. It's just the same thing again and again. That's all. And then just to illustrate it a little bit, right here. So another way to think about this problem is by remembering that 30 degrees is equal to pi over 6. Because 15 degrees is equal to 1/2 30 degrees, we can find that 1/2 times pi over 6 is equal to pi over 12. Same thing, right? Feel like you guys get that, so let's jump to something else. So I want to talk about finding coterminal angles. This is important, all right? So converting between degrees and radians can make working with angles easier in some applications. For me, all applications, but I'm different, right? So for other applications, we may need another type of conversion. Negative angles and angles greater than a full revolution, excuse me, are more awkward to work with than those in the ranges of 0 to 360 or 0 to 2 pi, however you want to take it, right? It would be convenient to replace those out of range angles with a corresponding angle within the range of a single revolution, right? So let's talk about that. Yeah,
I can talk about, full rotation,
yeah,
pretty sure that's a simple, but I said full rotation.
Yeah.
One.
right,
Like, you know, 100,
Yeah.
100,
exactly,
40 degrees or whatever.
right, exactly. You know? Building it all up. So it is possible for more than one angle to have the same terminal side. So let's looking at this figure right here, right? The angle of 140, right, is a positive measure measured counterclockwise, right? Counterclockwise. The angle of 200 negative, excuse me, negative 220 degrees, right, is a negative angle measured clockwise, right? But both angles have the same terminal side, right? They have the same ray over here, right? If two angles in standard position have the same terminal side, they are coterminal angles, right? Every angle greater than 360 or less than 0 is coterminal with an angle between 0 and 360 degrees. And it is often more convenient to find the coterminal angle within the range of 0 to 360 than to work with the angle that is outside of that range. Right? Mhm.
Recently, might as well plug in,
Yeah, yeah. Say you had 540, then you would just minus 360 from that to get the coterminal. Yeah.
Basically the inverse of a certain, right?
It's not an inverse. So it's the same terminal like side that we have, but I'm trying to find a more easier reference that I can use within 0 to 360. So instead of me having like 700 or like 720 degrees, right? I want something that's nice, like 30 degrees or 60 degrees, you know? So I'm trying to figure out what angle would be the coterminal to it, right? Coterminal being between 0 and 360. Yeah. Yeah. All right. My fault.
But David from the basis of negatives, when they're the negative side, you know, the conversion factor doesn't negative to land up.
It stays negative. Like if it's already negative, it'll stay negative. Like a negative degree.
And the 180 negative man.
No.
Myself.
No. Yeah. All right. Any angle has infinitely many coterminal angles because each time we add 360 to that angle or subtract 360 from it, the resulting value has a terminal side in the same location, right? So for example, 100 degrees and 460 degrees are coterminal for this reason, right? Hold on one second. Right? As is negative 260 degrees, right? Recognizing that any angle has infinitely many coterminal angles explains the repetitive shape of the graph of trigonometric functions, right? So any angle's reference angle is a measure of the smallest positive acute angle T prime, right? Formed by the terminal side of the angle T and the horizontal axis. Thus, positive reference angles have terminal sides that lie in the first quadrant and can be used as models for angles in other quadrants, right? So let's look at this figure. We have quadrant 1, right? Where T prime is equal to T right here. Quadrant 2, where T prime is going to be 180 minus T. That's how we're going to get this angle right here, 180 minus T, right? Quadrant 3, if we want to get that angle, right, it's actually going to be 180 plus, right, whatever T angle they got. Oh, no, sorry, T minus 180, because T is going to be bigger. That's true. T minus 180, because T is going to be bigger. That's how you're going to get this little angle right here for T prime. In the fourth quadrant, right, that's where you're going to do 360 minus a T to get that coterminal angle. All right. Questions on this? Long story short, add 360, subtract 360. That's another coterminal. All right. On your homework, you're gonna have some questions like that. You're gonna give you some angles, just add 360 or subtract 360. Pretty much. Yeah. A lot more. Yeah. There's a lot more. Yeah, there's a lot more. I'll add them. Don't worry. I'll add them. A lot. More than 5 was a lot. Yeah. Not 500. Less than 10. Less than 10. Yeah. Don't worry, it's not that bad.
Very much of these things.
If it's really, really easy, yes. If it's really, really complicated, no.
Yeah.
Yeah. Hmm. So coterminal and reference angles, all right? Pay attention to this part. I always get this confused myself right here, right? Coterminal angles are two angles in standard position that have the same terminal side, right? The same terminal side. An angle's reference angle is the size of the smallest acute angle T prime formed by the terminal side of the angle T and the horizontal axis. All right. So that's the difference right there.
Okay, so think about this angle would be initial angle.
It's kind of it's what I want. It's what I want between the terminal side and the horizontal axis, right? The x-axis is whatever angle that is, you know? Like, for example, right? You see how I have in quadrant 4 right here, right? I have this angle T that goes all the way around here and goes into quadrant 4. Cool. But the reference angle, the one that I'm really, really interested in, is the other side, right? Where the T prime is, all the way to the horizontal axis. Right? That's the reference angle. You know, right, reference angle. That's really, really important. That's gonna come in clutch. Not gonna lie. So here's an example, right? This is finding an angle coterminal with an angle of measure greater than 360. Right? So this is what happens when the angle is bigger than 360. So we want to find the coterminal angle for 800 degrees, right? It's going to be crazy right here. So 800 degrees, all right? That's what our pizza bakes at, I think, right? So, what I want to do, right? I want to find that coterminal angle. So what am I going to do? Subtract 360 from this. So what's 800 minus 360? 440? Okay. Now here's the thing, 440 is still bigger than 360. So subtract 360 again, what do you get? 80 degrees, right? So where would 80 degrees be? It'd be in the first quadrant, right? So this little angle right here with the horizontal, the x-axis, excuse me, and the terminal side, this is 80 degrees. Right? Huh? Well, yeah, it's a little higher, but I'm not an artist. You're right. It is a little higher. All right. So look, 800 is actually more like this. That's 360. Come around again. That's the 720, right? And then we go all the way up here. Bam. Right? So you see that's more complicated to work with than a little reference angle at 80. I'm sorry? Yeah. Mm-hmm. Just to get it. There is. That's coming. That's pending. Yeah. Right. But the purposes for this assignment right here, this part, I wanted the 80 degrees. And I wanted to see the terminal side right here. So if I had to like highlight the answer, like this would be my answer, like this part. Just showing you. All right. Yep, that's it. That's the co-terminal. I would love to see this workout though, so that I know that it's 80, you know? Yeah. Yeah, I could. That means it's gonna go counterclock. Yeah, same thing. Same thing. Yeah. It'll reach. It'll always reach. Yeah, it'll always reach. Yeah. It'll always be in reference to 360. Look, one. Yeah, it'll just be negative. It just starts the other way. Yeah, clockwise. Yeah. Let me give you a little how-to real quick. So given an angle with measure less than 0 degrees, find the coterminal angle having a measure between 0 and 360. So what you want to do is first add 360 to the given angle. If the result is still less than 0, add 360 again until the result is between 0 and 360. The resulting angle is coterminal with the original angle. Right? Good stuff, good stuff. I'm sorry? No inverse. That's it. If it was in radian, then yeah. You would flip it back, yeah. Since you asked about it, let's look at this example. So finding an angle coterminal with an angle measuring less than 0, right? So this is negative 45 degrees, right? So check this. Hold on, let me get my pen. So check this out, right? So negative 45 degrees, right? This is 0 right here. This would be negative 90, negative 180, negative 270, right? And this is negative 45. So I know that negative 45, I'm sorry, I didn't mean to do that. I know that negative 45 is right here, right? That's negative 45 degrees, right? But I want the coterminal one. So how could we get that? What do you think? Just add 360 to it. That's it, you know? So 360 plus negative 45 is what? What is it? 335? 25? Oh, 325, you mean? 350? 315, okay. All right, so that means that the coterminal angle will be this one. 315 degrees. And that's it.
That's what I was saying.
Yeah. What do you mean? Oh yeah, it doesn't go around full. Well, if I added another 360 to it, it would. Yeah, yeah. On your homework, there's gonna probably ask you for 3 coterminal angles or something like that, or 4, right? All you do is just 360, 360, 360, or if you want, minus 360, minus 360, whatever you like to do. You know? And then last thing. So finding coterminal angles measured in radians. So we can find coterminal angles measured in radians in much the same way as we have found them using degrees. In both cases, we find coterminal angles by adding or subtracting one or more rotations. All right. Like pi and 2 pi. Yeah, yeah. So given an angle greater than 2 pi, you're gonna to find a coterminal angle between 0 and 2 pi, you can subtract 2 pi from the given angle. If the result is still greater than 2 pi, subtract 2 pi again until the result is between 0 and 2 pi. All right. The resulting angle is coterminal with the original angle. All right. Me personally speaking, I don't do this. I flip it into degrees and I do the previous step. And then when I get my answer, I flip it back into radian and then call it a day. Right? Your choice, what you want to do. I personally don't like radians, I like degrees. You know? That's just my little tidbit. So if it was me doing this example for like real quick. So this is trying to find a coterminal angle right here, right? What I would do first is I would say 19 pi over 4. I would multiply that by 180 over pi, right? And then this is like 1, and that's what, 45? Then I would do 45 plus 19 times 19, excuse me. So I got 855, right? So I know it's 855 degrees. That being said, what am I going to do? Subtract 360 from it. Let's see what that is. $495. All right, $495. Give me another one. What is it? 135? 135? Okay. All right. So what's that's telling me, right? 135 I know would be in what quadrant? This is 0, 90, 180, right? The second one, right? 270, right? But I really can't write those numbers there. I really got to write the radians, right? So technically, this should be pi over 2, pi, right? 3 pi over 2, right? So 2 pi over 2, 3, yeah. So then now 135 we know is here. right? I know that my original one was 19 pi over 6, which was, let's see, two revolutions around. Let's start here. 1, 2. Come right back over here. So that's the 19 pi over 4, right? But the terminal one that I found, let me do that in like blue or something, which starts like here, then goes right here, right? That one would be whatever 135 in radians is. So let's do that. 135 times pi over 180. What's 135 divided by 180 in fraction form? What is that? 2.56? No, I want a fraction. Yeah. Don't put the pi. 135 divided by 180. 3, right, that's it. So 3 pi over 4. So that means that this is the reference angle, 3 pi over 4. That's how I would do it. All right. Exactly. You know, like radian is just like confusing to me. My fault, my fault. One last thing, one last thing. So determining the length of an arc, all right? So recall that radian measures theta of an angle was defined as the ratio of the arc length S of a circular arc to the radius R of a circle. So theta is equal to S over R. For this relationship, we find the arc length along a circle given an angle. All right? So here you go. You're going to see this on your homework as well. So in a circle of radius R and length arc, which is S, right? Subtended by an angle of measure theta in radians, right? To be clear, the angle is going to be in radians, right? Here is your arc length formula. S equals R theta, all right? The arc length is this part of the circle that you're trying to measure, right? Radius, you know what that is, from the center to the end of the circle. Theta is the angle of rotation, all right, around. And that's it. Mhm. Exactly. Yeah. So if I'm asking you what S is, you find what S is. You know, if I give you R and theta, or if I give you S and R, you find theta. Yeah. Same thing.
It's the same.
Same thing. Yeah. Same thing. So given a circle of radius R, say we want to calculate the length, the arc length S, right, of the arc, right, subtended by a given angle of measure theta. If necessary, convert the degrees theta to radian, then multiply the radius by the radian measure of theta, right? And then you get S is equal to R theta. That's it. That's how you find arc length. Right? The key thing there, right, is to switch the angle, right, into radian. Right? Let's just do one example together, then we could call it at that. So in this question, we want to find the arc length along a circle of radius 10 units subtended by an angle of 215 degrees. My only issue here is I have the angle in degrees, switch that to radian, right? So let's do that. I know what my radius is, that's 10, right? But for my angle theta is 215 degrees. I want to multiply that by what again? I forgot. Other one. Pi over 180, right? That's the one to go to radians, right? Pi over 180. Multiply straight across. Help me out. 215 divided by 180 is what? 180. Switch that into a fraction. What is that? There's a button on your calculator that does it. Okay, so 43 over 36 pi. Right? So now what's our formula? Arc length, S, is equal to R theta. Right? So for us, what do we have? We have 10 times 43 pi over 36. That's simple, right? Let's see. I could factor 2 out of this, make that a 5, make this what, 18, right? So this is like 43 times 5 pi over 18. Help me out. What's 43 times 5? 215? All right, so 215 pi over 18, I guess. Yeah. Yeah. Does 18 go into 215 evenly? I don't know. It doesn't. Almost, yeah. It's all right. So that would be it. 215 pi over 180. Okay. And that's the arc length. Okay. You could type it in just like that in WebWork. I think on the right-hand side they got the pi symbol. If you don't see it, yeah, if you don't see it, just type PI. Yeah, let's see. All right. It's been real. Great night. Monday, let me get that test back. All right. I mean, I hope y'all do. No corrections on this one. Good. Huh? Good. Uh-huh. Wait, say.
Correction, I just did one.
Yeah, that's